For nearly 5 decades, NASA's Voyager 1 has embarked on one of the most remarkable journeys ever undertaken by humankind. Launched in 1977, it was designed to explore the outer reaches of the solar system, venturing beyond the planets and pushing into the vast, uncharted expanse of interstellar space. This spacecraft holds the record as the farthest human-made object from Earth, and with every passing year, it continues to defy expectations, providing invaluable data about the cosmos. Its mission, which was originally intended to last only a few years, has extended into a journey that no one could have anticipated, spanning the decades and revolutionizing our understanding of the universe. However, in an unexpected twist, Voyager 1 recently began transmitting mysterious and garbled signals that baffled scientists, prompting fears that its legendary journey had come to an end. After over 45 years of success, many speculated that the spacecraft had finally succumbed to the extreme conditions of deep space. But just when it seemed like the mission might be over, NASA confirmed something truly remarkable. Voyager 1 had resumed sending back usable data, defying the most dire predictions. The data it transmitted wasn't just routine. In fact, according to one Nobel Prize-winning scientist, the information that the spacecraft is now returning could be far more profound than anyone expected. It might even contain evidence of an anomaly that could challenge everything we thought we knew about deep space, potentially offering new clues to the structure of interstellar space or even revealing previously unknown cosmic forces. The possibilities are endless, and this development has left the scientific community buzzing with speculation. As scientists scramble to decode this unexpected data, there is growing anticipation that Voyager may first have stumbled upon something extraordinary, something that could completely alter our understanding of the cosmos. Could it be detecting a phenomenon that has never been encountered before? What could this mean for the future of space exploration? These questions loom large as Voyager 1 continues its lonely journey through the depths of space. Its mission, once thought to be nearing its end, may now be on the brink of uncovering one of the most significant discoveries of the 21st century. Part of the Voyager mission's greatness lies in the unprecedented strategy behind its trajectory, a carefully planned path known as the Grand Tour. This mission took advantage of a rare planetary alignment that occurs only once every 176 years. Planets orbit the Sun at varying speeds, meaning they are typically not positioned in such a way that would allow a single spacecraft to visit multiple worlds. But in the late 1970s, NASA scientists discovered that the planets Jupiter, Saturn, Uranus, and Neptune would align in a way that would allow a spacecraft to visit all of them using a series of gravity assists. This incredible opportunity would give Voyager 1 and its twin, Voyager 2, the ability to travel vast distances with minimal fuel consumption, an essential factor given the immense distances involved. At the time, the idea of a grand tour seemed like a distant dream, too complex and costly to be feasible. But with advances in technology and a bold vision, the mission began to take shape. The carefully timed launches of Voyager 1 and 2 would maximize the gravitational slingshot effect, allowing the spacecraft to gain speed as they passed each planet, using the gravity of these massive worlds to slingshot them toward their next destination. Each encounter was meticulously planned, with each spacecraft using small engine burns to adjust its course and meet each planet at the perfect angle and distance. This intricate planning meant that both spacecraft would gather detailed data on their flybys, which would inform the future of space exploration. While Voyager 2 was launched first in August 1977, it was Voyager 1 that took the faster, shorter trajectory, making it the first to arrive at Jupiter. Its speed and path would allow it to explore Jupiter and Saturn in far greater detail than its counterpart. Voyager 1's close encounter with Jupiter took place in March 1979, a moment that would reveal the gas giant in all its majesty, offering up stunning images and groundbreaking scientific data. Voyager 2, following a more leisurely route, would pass Jupiter several months later, in July 1979, but would continue on its way to Uranus and Neptune, worlds that had never before been explored. Jupiter, with its enormous size, more than 11 times the diameter of Earth, was an exciting target for exploration. NASA had only a limited understanding of the planet, with earlier spacecraft, such as Pioneer 10 and 11, offering only a glimpse of its mysteries. Voyager 1's flyby would dramatically increase our knowledge of the planet, uncovering a wealth of new information. The spacecraft captured breathtaking images of the planet's Great Red Spot, a massive storm that had been raging for centuries, and provided detailed insights into Jupiter's intense radiation belts, its atmosphere, and the swirling cloud patterns that dominated its surface. One of the most unexpected discoveries came from Io, one of Jupiter's moons. Scientists were stunned by the active volcanic activity on Io, which was far more intense than anyone had anticipated. Volcanic plumes of sulfur-rich material erupted high into space, revealing that tidal forces from Jupiter were driving the moon's geological activity in ways that no one had expected. Meanwhile, Europa, another of Jupiter's moons, presented an entirely different mystery. Its smooth, icy surface suggested that beneath the frozen crust lay a vast ocean of liquid water, an exciting prospect for future exploration, as scientists began to speculate about the potential for life hidden beneath the ice. In addition to these discoveries, Voyager 1 revealed previously unknown features of Jupiter's ring system. While Saturn had long been famous for its striking rings, Voyager 1's flyby revealed that Jupiter, too, had a faint ring system of its own. These rings, though much dimmer and less prominent than Saturn's, were an important discovery that would broaden our understanding of how planets and their moons interact with one another in the solar system. This groundbreaking mission, which began with the grand ambition of exploring the outer planets, has now extended into uncharted territories. Voyager 1's journey through interstellar space, far beyond the reach of the Sun's gravitational influence, continues to send back data that challenges our understanding of the universe, and the recent discovery has only added to its legacy. As the spacecraft drifts farther away from Earth, its data continues to offer new insights that could shape the future of space exploration for generations to come. Voyager 1's mission is far from over, and with each new revelation, we are reminded of just how much we have yet to learn about the cosmos. The discovery of Saturn's intricate and enigmatic features sparked a surge of wonderment, reshaping our comprehension of the outer planets. Saturn, a ringed world, had captivated astronomers for centuries, with its iconic rings always being a subject of fascination. Even through Earth's modest telescopes, the sight of Saturn's rings was a striking and awe-inspiring spectacle. But it wasn't until the Voyager missions reached Saturn that scientists truly began to grasp the complexity of this planet and its moons. Before these groundbreaking missions, Saturn's rings were seen only from a distant perspective, and while Pioneer 11 had given us some insights, they were far less detailed than what Voyager would reveal. Voyager 1's arrival at Saturn in late 1980, followed by Voyager 2 in 1981, brought forth revelations that exceeded the expectations of even the most optimistic scientists. These spacecraft delivered high-resolution images that unveiled the true nature of Saturn's rings. Rather than just broad, uniform bands, the rings were composed of an incredible array of countless small particles. Some of these particles were as small as grains of sand, while others were as large as boulders. The rings themselves were not static but dynamic, showing intricate structures such as thin ringlets, gaps, spokes, and waves, features that hinted at the underlying gravitational interactions between the particles, the moons embedded within the rings, and Saturn's larger moons. Shepherd moons were identified, showing how these small bodies played a vital role in maintaining the sharp edges of the rings, acting as cosmic gardeners in an ever-evolving dance with Saturn's gravitational pull. In addition to Saturn's dazzling rings, Voyager's close examination of Titan, Saturn's largest moon, was another highlight. Titan, a moon so vast it surpassed the planet Mercury in size, revealed a thick, hazy atmosphere composed largely of nitrogen and organic compounds. The haze on Titan was so dense that even Voyager's sophisticated cameras could not capture its surface. However, the spacecraft did collect crucial data, which suggested the possibility of lakes or seas composed not of water, but of methane or ethane. This speculative hypothesis was later confirmed by subsequent missions, such as Cassini-Huygens, which observed actual liquid hydrocarbon lakes on Titan's surface. Titan quickly became one of the solar system's most intriguing bodies, not only due to its rich atmosphere, but also because its chemical makeup led some scientists to consider it an analog to early Earth, a place where the building blocks of life might have once existed. Other moons of Saturn also surprised scientists with their unique characteristics. Mimas, with its massive Herschel crater, came into sharp focus. This moon's distinctive appearance made it look like the Death Star from Star Wars, forever linking it to pop culture. Enceladus, another of Saturn's moons, turned out to be highly reflective, suggesting an icy surface. While Voyager's instruments did not detect the geysers that would later be confirmed, they did uncover intriguing surface features on other moons like Tethys, Dione, and Rhea. These findings contributed to an expanding understanding of how icy moons in the solar system had evolved over time. At the same time, mission planners faced tough decisions as they navigated the complexities of these flybys. Voyager 1, after completing its observations of Saturn, altered its trajectory to get a closer look at Titan, but this decision meant that it could not continue its journey to Uranus or Neptune. Voyager 2, on the other hand, remained on course to explore the outer reaches of the solar system, ensuring that it would make historic flybys of both Uranus and Neptune after Saturn. The data gathered from Saturn by both spacecraft reshaped our understanding of planetary rings, moons, and the environment of gas giants. Voyager 2's subsequent flybys of Uranus and Neptune were the only such visits from a spacecraft, making these encounters invaluable. Uranus, with its peculiar axial tilt, was an intriguing target. It orbits the Sun at an almost horizontal angle, rolling on its side. Voyager 2's visit in January 1986 revealed a more complex ring system than previously thought. Although these rings were darker and less expansive than Saturn's, their discovery was pivotal in expanding our knowledge. The spacecraft also uncovered 10 new moons and revealed that Miranda, one of Uranus' moons, possessed one of the most bizarre surfaces in the solar system, marked by deep canyons, scarred terrains, and patchwork geological features. Miranda's surface suggested a tumultuous and chaotic history. Another surprise was Uranus's magnetic field, which did not align with the planet's rotation axis. This anomaly suggested unusual processes occurring deep within the planet's core, further complicating scientists' understanding of the ice giant. After completing its exploration of Uranus, Voyager 2 continued its journey to Neptune, where it arrived in August 1989. Neptune, like Uranus, turned out to be a world of unexpected wonders. The planet's dynamic atmosphere, which displayed a great dark spot similar to Jupiter's great red spot, was a particularly striking feature. Bright, rapidly moving clouds also darted across high latitudes, giving the planet a vivid and active appearance. Neptune's largest moon, Triton, was found to have a thin nitrogen atmosphere and geysers of nitrogen-rich material erupting from its surface. These geysers pointed to a geologically active moon, and the fact that Triton orbits Neptune in the opposite direction of the planet's rotation suggested that Triton had been captured by Neptune's gravity in the distant past. Both Uranus and Neptune, often overshadowed by the more famous Jupiter and Saturn, proved to be fascinating worlds in their own right. Voyager 2's findings helped refine models of ice giant composition and opened up new questions about their formation. The presence of water, ammonia, and methane ices in their interiors indicated that these planets had evolved along a different path compared to Jupiter and Saturn. The data also suggested the possibility of deep ocean layers within these planets, layers that might influence their unique magnetic fields. Voyager 2's flyby of Neptune was a crowning achievement, marking the successful completion of its primary mission. After this August 1989 encounter, the spacecraft continued its journey into the farthest reaches of the solar system, having fulfilled all of its objectives and provided transformative data about the outer planets, their moons, and their ring systems. Meanwhile, Voyager 1, having already completed its flyby of Saturn, left the plane of the planets and began a journey that would eventually lead it into interstellar space. Both spacecraft, through their carefully planned trajectories, have remained unparalleled in their contributions to our understanding of the cosmos. As Voyager 1 continues its journey into the unknown, it sends back invaluable data that challenges previous assumptions and opens new avenues of scientific inquiry. Beyond Neptune lies the Kuiper Belt, a vast region populated by small icy bodies. Even farther out is the hypothesized Oort cloud, a reservoir of comets stretching nearly halfway to the nearest stars. Yet, one of the most intriguing frontiers beyond Neptune lies in the outer boundary of the solar system, where the solar wind begins to interact with the interstellar medium. This boundary zone is complex and includes multiple layers such as the termination shock, the heliosheath, and the heliopause. The heliosphere, which is the region dominated by the solar wind, is shaped by the flow of charged particles emanating from the Sun. As these particles travel outward, they eventually encounter interstellar plasma, which slows them down and forms the termination shock. Beyond this shock lies the heliosheath, a turbulent region where the solar wind is compressed and heated. At the very edge of the heliosphere, the heliopause marks the boundary where the solar wind's influence is overpowered by the interstellar medium. For years, scientists debated where exactly the heliosphere ends. Although it was known to extend beyond the orbit of Pluto, the precise boundary remained uncertain. However, the Voyager spacecraft, equipped with instruments capable of detecting changes in particle flow and magnetic fields, provided the answers. As Voyager 1 crossed into interstellar space in 2013 and Voyager 2 followed in 2018, these transitions became historic milestones in space exploration. Both spacecraft detected unexpected turbulence and changes in plasma and cosmic rays as they passed through the heliopause, marking the first time that human-made objects had ventured beyond the protective bubble of the solar wind. The discoveries made by Voyager 1 and Voyager 2 continue to rewrite our understanding of the solar system and beyond. Their journey is a testament to the ingenuity and perseverance of the engineers and scientists who designed them. As these spacecraft continue to travel farther into the unknown, they challenge our understanding of the universe, unveiling mysteries that have never before been touched by human exploration. These missions have forever altered the way we perceive our place in the cosmos, proving that the boundaries of exploration are always expanding, and that the pursuit of knowledge has no end.